Yeah, so like that.
Let's start with the business packet, please. Start with the business packet, please. All right. So yes, you do that. All right. So we have a quiz on Friday. 3 sections on the quiz. First section that's on the quiz, section 4.4, parametric equations. There were 3 main things on parametric equations we had to know. The speed equation of the particle, the slope of the path of the particle, and then understand that x and y are the horizontal and vertical position of the particle, and therefore x prime and y prime would be the horizontal and vertical velocity of the particle. And then be able to answer questions using that information. Be able to graph it onto your calculator, be able to trace a point, parametric mode, be able to calculate slope, speed, do those kind of things. All right, so that's that. And we'll talk more about that as the week goes on. Section 4.3 was optimization, so that was maximum and minimum. And there are 3 places that a function can have its max. Endpoints, where the derivative is 0, where the derivative is undefined. And so we have to discuss those, find those, set up the problems that we're trying to maximize or minimize, and that's what the business packet was about. We're talking about profit, revenue, those kind of things, maximizing that. So we'll be doing those kind of problems more as we go throughout the next couple of days. And then this new thing we learned yesterday, related rates, which is all about how fast is this changing when this is changing and this other thing is changing, and they're all related. We have to set up the equation, we have to find those. And it involves x primes and y primes and r primes and h primes and y primes and a primes and whatever. All the different things that are changing. It uses implicit differentiation, which is a different kind of doing the derivative than in the max-min problem. The max-min problems, we set up a function, we want to get just one variable, and we want to then do the derivative, set it equal to 0. In related rate problems, we just need to get an equation. And it might have x and y and z, or a, b, and c, or volume and r and h. It might, depends on the problem. It might have all those different variables in it. And then we do the derivative with respect to t, time. And we do implicit differentiation, and we might have r, but we're not setting something equal to 0 and that kind of thing. All right, so there's differences in how those problems look. So we'll go through those kind of situations here a little bit. So we look at the business packet first, and in the business packet, we have these formulas right here that I don't know that you really need to memorize any of these formulas so much as, maybe the one for sure would be profit is revenue minus cost. Revenue is the money you bring in, cost is the money that you pay out, and then profit is the difference. And hopefully your revenue is more than your cost. So the profit is positive, right? And you're not losing money. This one, I'm not sure I would memorize this x times p thing. I think you should memorize the fact that revenue comes from selling so many units at a certain cost per unit. So p they call the price function, or in the problems, Steve, to answer your question, the demand function that they call, sometimes the price function is called the demand function because the price of a product is often dependent on the demand. High demand, you can charge more, okay, for the product. So you take P, the price, times how many units you have, okay, and that's your revenue. And then your cost is, your cost. Usually in the problem it tells you the various things that contribute to the cost. And then you've got this one, this average cost per unit. You just take your total cost divided by x. And they call that C bar. And then we have this idea about marginal cost, marginal revenue, marginal profit. I wanted to make one point about this equation right here. The max profit, if you start up a business, okay, let's say you open up a coffee shop, right? Well, in the beginning, you've got cost. You've got to buy the equipment, you've got to pay employees, you've got to buy materials, to make the coffee and all this kind of stuff, pay rent on the building, right? So you're going to start in the negative, right? So your profit will be negative. You'll be behind. You'll be in debt because your costs outweigh your revenue. But then as you start getting customers and making money, okay, your profit will start to come up, or at least you'll get closer to breaking even. Now, the break-even point would be when your revenue equals your cost, right? If profit is revenue minus cost, well, when revenue equals cost, you do revenue minus cost, that would be zero. Your profit will be zero, but at least you won't be in the hole. That's called the break-even point. After that, your profit is increasing because now your revenue is hopefully greater than your cost, and now your profit is increasing. But what you would like to do is know how many stores would you open, or how much coffee do you need to sell, which might mean how late do you need to be open, what days do you need to be open, whatever, how big does your building need, how many machines do you need, whatever, to maximize the profit. So the more you sell, the more you make. But at some point, if you have to open another store or buy another machine or hire more workers, maybe that's not profitable. Maybe your profit actually starts to go down after that point. Okay? Because you're not selling enough to keep up with those additional costs. This is called the marginal profit, is the derivative. Marginal profit's a derivative. So max profit happens when your marginal profit is what? Zero. When the derivative is zero. So when business people, managers that would be working on these kinds of things, and if you have a management degree, a college roommate of mine got a management degree, and he had to take applied calculus, and a lot of his management classes used a lot of mathematics and statistics in there because they gather data on, on the market and what they think they could sell and at what price and so forth. And they try to hit this maximum profit. And they want to, and so one thing they talk about a lot is marginal profit. Okay, if we sell this many, what's our marginal profit? Well, if it comes out positive, what's that mean? If the marginal, well, yeah, but if the marginal profit's positive, what's that mean? That means your profit is increasing. It means you need to sell more, right? I mean, that's good. Your profit's positive, but that just means you're making money. If the marginal profit's positive, that's from the chart, right? Basically what you're saying is the derivative is positive. It means the profit's increasing. So you'd be in here somewhere, right? So if the marginal profit's positive, it means sell more. If the marginal profit's negative, it might mean sell less. In other words, that might mean you're still making profit, but your profit's actually decreasing, right? Because you've taken on maybe additional costs and you're not selling enough to offset those. And so the max profit would happen when the marginal profit is zero, okay? And so now how do they get these equations? Well, they're not cut and dried. I mean, our problems are overly simplistic right now, so we can go through the process. But most real-world kinds of mathematical models they use is based on data they collect from years of sales and trends and what people are buying now and so forth. And that's why they use surveys and they do, those kind of things. Okay, so that's where this stuff would come from. All right, so we go into, well, which problems did you want to look at here? On 19 and 20, obviously, we want to talk about a little bit. But what about in these here? 15. Okay, come on. Now, I will make that comment back here about demand function. This little p, that's your price function. But they call it the demand function. Well, that's because price is based on demand, right? So this little p is your price function. So what you need to do is take this times x. Oh, and one other comment I want to make, because somebody came in and they did this on their calculator and it was giving them an error. So I want to make sure everybody's aware of this. They were doing their profit function, which is revenue minus cost. So they did their revenue, which is x times their price function, which is this. Okay, so this would be their revenue, minus the cost, which is, they give you the cost function here. Okay. And they put that in their calculator to have the calculator simplify it, which I think is a great idea. Put this in your calculator to have it simplify it for you. You just type it in and it'll just do it. And then take that and do the derivative, because we want to do when the derivative is zero. And then solve it and find out where that is. But they were getting an error right here. Anybody know why? Yeah. Right here, you've got to put a time sign. What it thinks is you've got the function x of something. And it doesn't know you mean time. So you need to put in a lowercase sign. Okay, so you do the derivative. You should write out what that derivative is, set it equal to 0, then you get x equals, and so forth. So let's go to 15. So this is the demand function, so we're going to take that times x. That's our revenue. and then we're going to subtract our cost. 40x plus 37.5. Okay, so this is our profit equation. The price times x minus all this, that is our profit equation. So now what price yields the maximum profit? So we do P prime, whatever that comes out to be. We get x equal, let me see, I think I got that here. 6.325. But then they wanted to know what price. So you have to put that back here into your price equation. Okay? So you take 6.325, put it back into the price equation, it comes out to be $80. So a price of 80 would get the max profit. Now I didn't do any justification there that it's a max. So we got to be careful here and do this. Now as I was going around and looking, I saw that was missing on a lot of papers. Hopefully that just means you were just kind of assuming that's the max. But on the quiz, you would be more careful and show either a list of candidates. Now, a lot of these problems, because we've simplified them down, a lot of these max-min problems, we're getting only one candidate. And that's fine. But what you should have done right here when you got this one candidate is you should have done a number line, P prime, 6.325, put a 6, put a 7, put that back into your P prime equation, show that you got a positive and a negative, and that means it's a max. And technically, we should say it's always increasing before and always decreasing after, and that's why, or maybe you don't really have any influence there. But there's got to be some discussion that it's a max, okay? Now, on the quiz, if you didn't do that, it might only cost you a point, 1 out of 4 or 5 maybe. But, let's be in a habit of justifying that we have a max there. All right, and then when the profit is maximized, what's the average cost per unit? Well, remember, average cost per unit is the cost equation divided by x. And then that means you put in a 6.325. So put a 6.325 there and for your cost, and then divide by 6.325. That's your average cost per unit. Average cost per unit. Okay? All right, let's go into 19 and 20, and let's talk about those a little bit. Now, since I did have the answers online where you could look at, maybe many of you were able to look at that and maybe figure that out. But the key here is, because the business problem that would be on the quiz, if there's 1 or 2 business type problems on the quiz, they would look more like 19 and 20. Okay, that's the type of problem it's going to look like on the quiz. All right, so you've got to be able to set these things up. Now, after going through a couple of these and doing it for a couple of days, I think they get easier. Now, normally, let's do number 19. Normally, we talk a lot about X being the number of units. Okay? The number of units that we're selling, that we're making our money off of. Now, it doesn't have to be that way. That's why I'm saying to you, I don't think I would memorize this revenue equation as X times P. What that really means is number of units sold times the price per unit. That's what you should memorize. Number of units times price per unit. That's what you need to memorize. All right? So let's talk about this problem with the radios. All right? How many radios are we going to sell? Well, we don't know. I mean, we don't know the number. But, I mean, what's it say? There's a cutoff of how many radios. 100, right? If they'll order more than 100 radios, we're going to do what? We're going to give them a price break, right? We're going to give them a price break. Okay, very common thing. Larger orders, you can get it a little cheaper. So we're going to take that $90 price and we're going to cut it by 10 cents. Now, I had a few people ask me, does that mean just the ones over 100 are cut by 10 cents? No, it's all of them. So if you buy 100 radios, they're 90 bucks a piece. If you buy 101 radios, they're $89.90 a piece. Okay, all 101 of them. Okay, so let's let X be the number of radios. Okay, so now? Did anybody go back in the packet and look at the example? They did an example. A few people in the other class did, and they kind of wrote it like a slope-intercept form, and I never really thought about doing it that way. I just kind of thought about thinking my way through the problem. So let's talk about the price first, little p. let's talk about the price of the radio. So what's the radio price going to be? Well, the base price is 90. Now this is if it's less than 100, right? But let's just assume it's going to be more than 100, right? So then we're going to subtract 10 cents. Now we got to be careful. I don't think it's 0.1x. Yeah, it's only for the ones over 100, right? So wouldn't that be x minus 100? Okay? Because we're only going to subtract 1 dime off if it's 101 radios. So what we need is 10 cents times 1 here. Well, the way to make a 1 happen here is if x is 101, right? We sell 101. So we need 101 minus 100. So that, and if we sell 102 radios, we'll take 20 cents off. Okay, so 102 minus 100, that's 2 cents, or 2 radios, or 2 10-cent price reductions. So this would be our price. This would be the demand function that they were talking about in those earlier ones. Okay, so as x gets bigger and bigger, we take off more dimes, okay, off the price. So that's the price of 1 unit. Okay, and then x is the number of units, right? So this formula works quite nicely. So our revenue then would be x times that whole thing. And then we could get on our calculator and have our calculator simplify that for us. It's not necessary to, but I think it's kind of nice. And then that's our revenue. Sorry, minus 100. Okay, and then that's our revenue. Okay, so x times our price, and we want the profit. So we need to subtract what? Every radio costs us $60 to build. So 60x, yes.
Well, what if you had like less than 100?
Okay, so here would be in this particular case, here's the assumption I'm making. This would be kind of like a piecewise function, in other words. So if x is 100 or less, then the price is just 90. And then I'm making what, 30 bucks a radio? Because the price is fixed at 90 and it cost me 60, so I'm making 30 bucks for every radio. So that's just a linear function. So every time I sell another radio, I'm making more money, right? So for under 100 or up to 100, the max would be to sell how many? 100, right? The max would be to sell 100, okay? So 100 radios times 30 bucks profit is what? 3,000? So I would look at 100 as kind of an endpoint, to be honest, in this problem. That'd be one way to look at it. 100 is like one endpoint. Because I know 0 and 1 and 2 radios is not going to be a max profit, right? I'm making 30 bucks on every one of those things. So every time I sell one, I'm making money. So I'm going to make more and more the more I sell, up to 100. But now, once I get over 100, now I'm knocking off a dime. So if I knock off too much money, I'm not going to be making as much, right? And so where does that happen? So that's what I'm thinking about when I set this up. I'm thinking about over 100 because I know up to 100, my max will be right at 100. Okay, so we go ahead and we do this, and now we do the derivative. So you did that in your calculator. I don't know, what did you come up with? Like 40 minus 0.2x. You set that equal to 0. You solve it. You get x equals 200. Now, you could do a number line here, but we probably do need to consider that 100 barrier, see what that is. You could do a thing here to show that, yes, that is a max, okay? But we do have, this could be appropriate to do a list of candidates situation too, and call 100 one of our endpoints, okay? Now we know that the number line would look like this. There's only one time the derivative is 0, so it's going to increase and then decrease forever and ever, right? So my profit's going to keep decreasing. Here'd be another thing you could do on these problems. Look at your profit equation. When you guys simplified it in your calculator, wasn't that a parabola? Isn't this an x squared? And it's a negative x squared, which means it's what? Upside down parabola. So, and some of these more simplistic equations, your justification could be that. You could say, hey, the profit equation is an upside down parabola. The max has to be when the derivative is 0. You know what I mean? When we talk about the derivative undefined, derivative 0, endpoints, but if it's an upside down parabola, I mean, the max is going to be at that vertex when the derivative is 0. All right? But here we might want to consider, what if we only sold 100 radios? Maybe we're knocking off a dime here, and that's going to cost us, and maybe that's not our max. So we already said we're making $30 a radio, so times 100, that'd be $3,000 profit. What do you get when you put 200 into this? 4,000. So that is more profit. So there is your max. And so 200 radios is what you should do. Okay? All right. Having the number line and having this list of candidates, whatever, is a little bit redundant, you know, but having too much information in the problem is way better than not having it. All right? Let's talk about number 20. We're going to rent some apartments. That's our revenue. We're the apartment owners. We're going to get revenue in by the rent. And then it costs us some money for the occupied apartments, right? I mean, might have to fix a hole in the wall. We might have to repair a carpet. We might have to, maybe the refrigerator goes out and we got to put in a new fridge or whatever. Okay, so that averages out, it says, to $36 a month for each apartment. Okay, so those are our costs. So we want to write our profit equation, revenue minus cost. Okay, so let's start with our revenue, our rent. Now, the problem with this one is, what are we going to let X equal? Well, what would the normal thing be to let X equal? Number of units, right? Number of apartments that are occupied. So the normal thing to do here would let X be number of occupied apartments. Okay? Now, every time, if we're full, we can charge $540 rent, right? But every time there's an unoccupied, well, it doesn't really happen in this order, but for every unoccupied apartment, what's the rent? Goes up $30. That's actually in reverse. Every time the rent goes up $30, one is unoccupied. In other words, the higher we make the rent, people may live somewhere else. Okay? But now that depends on a lot of things. It depends on demand. Like in Kearney, it's really hard to find places to rent. A friend of mine is in the property management business, and he said here a couple months ago, he said they couldn't find a single thing to rent. They had people come to town and want to rent some. There wasn't anything. Apartments everywhere. Everything's full. Okay? You know, so that means landlords could probably charge more, right? They could raise people's rent. Okay? Now you sign a lease usually, and that's good for a year, and so that's you know, they can't raise it in the middle of that. But then to sign a new lease, they say, hey, the rent's going to go up to this. You don't want to pay? Too bad. Go find another place, because they know somebody else will, right? Because there's a lot of people here. So the price would depend on a lot of different things. But so anyway. So let's talk about X is an occupied apartment. Okay, so revenue is the price per unit. So let's talk about that first. Let's talk about price per unit. So the price is going to be $540, but it's going to increase, right? So tell me what to put next. Plus. Okay, now. See, what a lot of times people want to put here is they want to put 30x. But why would it not be 30x? Because it's going to go up 30 every time something's unoccupied, right? So the first time we go up 30, we want this number here to be a 1. Well, the first time it's 30 is, how many occupied units do you have? 49, right? And so what we need is this to be 50 minus x. Because when there's 49 occupied apartments, so when X is 49, this will be a 1. So we'll have one $30 increase. When there's 48 occupied, when X is 48, this will be a 2. That'll be two $30 increases. Yes?
Okay, well, when I did this problem, I had X equal the number of times $30 goes up.
That's right.
So,
Yes, and I'm gonna show that in just a second, because I really think that's an easier way to understand this one. But you can do it either way. Our normal way of doing it is let X be the number of units of things we're making money on, which in this case is occupied apartments. So this is a way people might normally do it. So here is but I think sometimes that's a little harder to set up. So this is our revenue, right? No. That's the price for one apartment. Right? This is the price for one apartment. We need to multiply this times what? Number of apartments, which is, X, right? That's what X is, our number of occupied apartments. So we have to take our price, this is our little p right here. This is the price for one apartment times the number of apartments that are occupied. Okay, minus at every occupied apartment costs me $36 every month. So I got to subtract 36x. Now, the good part of letting x be the occupied apartments is this was easy. The number of apartments was just x, and the 36x, that was easy to write. This part was harder to write. So it's just kind of a trade-off. I'm not sure how much easier one is over the other, but it's kind of personal preference. So there you go. You would get this. Okay, so then you do p prime, whatever that is, and you set that equal to 0. That's got to be on your paper, though, right? Not like that. You got to write out the function. Set equals 0, and it came out to be 33.4. Now, what's wrong with 33.4? Can't have part of an apartment occupied, right? So what are we going to do with that? You you better round down and round up. You better do a list of candidates. It's not technically a list of candidates, but what we better do is figure out what's the profit if we have 33 occupied and what's the profit if we have 34 occupied. But technically, that's still just one candidate. How do we know that's a max, a max versus a min or whatever? Well, that's where, again, a number line could come in. Or you could look at this and say, hey, that's just a parabola. I mean, if you look at this profit equation, again, it's an upside-down parabola. So that is our max. But just to make sure, 33.4, we'll put numbers on here, 30, 40. It is a max, okay? So again, don't forget about that kind of justification. All right, so if I put in 33 into my profit equation, I know I got it here somewhere. It was 33,462 and 33,456. So just barely, but 33 is the one. Now, what did they want for the answer, though? Yeah, what should the rent be? Well, the rent was this right here, right? So I need to put a 33 in here. 50 minus 33, that'd be 17 price increases. 17 times 30 is 510, plus 540, 1,050. So to maximize profit, this scenario is saying that this person should leave 17 of theirs unoccupied and charge 1,050. Well, it really means he should charge 1,050, which might mean 17 of them will be unoccupied, but he'll still make more money. Okay? Now, if he can get 1,050 and get them all to be occupied, that'd be great. But again, it would depend on demand. And the demand in that particular area is saying that this is what would happen. That every time you go up $30, one will become unoccupied. Okay? All right. So that was one way to do it. So if we talk about what Natalie was just saying here, another way to address this would have been to let X be number of price increases. Now, usually in these business problems, this is what you're trying to decide. You're trying to decide what to set the price so that you'll maximize the profit. I mean, sometimes you might be trying to say how many to make, but usually how many you make affects demand and affects the price. Okay? So it really is more about what should we set the price at, how many can we sell at that price to maximize our profit. So often it is a good idea to let X be the number of price increases. One of your homework problems today, I think it's easier to set it up this way. Definitely on the one today. On this one, I think it was about the same. Okay, so you said, Natalie, for your revenue, you let the rent be 540 plus 30X, right? Because X is how many price increases. So one price increase at 30, two price increases at 60, and so forth. And then you're going to take that times, so that's the rent for one apartment. We got to take that times what? The number of apartments. Well, how many apartments are there going to be occupied? Well, every time the price goes up, you lose one apartment that's occupied. So that would be 50 minus X. So that part of it gets a little harder to write, whereas up here, the number of units was just our X. Okay? So there you go. Price for one unit, this would be the number of units. And then minus the cost. Well, the cost is 36 times the number of occupied units. What's the occupied units? 50 minus x, right? So that made that part a little more complex as well. But now, okay, again, keep in mind, since x is a number of price increases, one price increase, when x is 1, 50 minus 1, that's 49 units, okay, that are occupied, and so you have to do that. Now you do your derivative, set it equal to 0. This time you get x equals 16.6, right? Well, when x is 16.6, that means there's that many pricing. Well, you can't have half a price increase, so you check 16 or you check 17. Well, you can see that's what we said here. 16 or 17 price increases means 16 or 17 unoccupied apartments, which would mean 33 or 34 occupied apartments. So when you plug those back in your profit, you get those same numbers, and you get the same result, 1,050. Okay? So I really like this idea, though, of thinking about sometimes not letting x be the number of units, letting x be the number of price increases or decreases. Okay, depending on the problem. All right, let's move on here to the related rate problem, and I want to talk about number 7. Was that the rectangle one? I want to talk about that one real quick, because I helped a lot of people who read number 7 and they put 2 meters per second here, 3 meters per second here, and then they put a 4 here, they put a 5 here. What's wrong with all that? Number one, well, these aren't constant. But somebody told me, well, yeah, but these are 3 meters per second and 2 meters per second are constant. The rate stays constant. That's true. But those are primes, right? We never, our picture should have x's and y's and r's and h's, and the only thing that's, the only number, the picture should have distances and lengths on it. Then those lengths and distances are changing, and those are the primes. And we need to set up equations. If we need an x prime and a y prime in our problem, we need an x and a y in the equation, not numbers. And so what should happen in this problem is, and Cassie said something to me this morning that made a lot of sense, and so I want to explain to you what she said. So in this particular problem, if I want to label this as my x and this as my y, and they give me the rate that x prime was 2 centimeters per second, and they tell me that y prime is, was it 3? So she's like, okay, well, I see that the rates are x prime and y prime, but why even tell me that x equals 4? Is that the right one? Does 4 go with 2 in this problem? Why even tell me that it didn't make any sense to her? Why do I have to put an x here and then over here say x equals 4? If x equals 4, why can't I just put a 4 there? Because it's not always going to equal 4. And that's the key. When I drag this bottom corner of this rectangle to make it grow, the question is asking this: how fast is the area changing at the instant that x is 4 and y is 5? So x is changing, y is changing. But there's going to come an instant when x is 4 and y is 5. And that is the instant I want to plug those numbers in. And that doesn't come until after I've done my derivative and all that. So I get my x and xy or y prime and x prime, all those in the problem. So that's why I write those over here and do not put those in my picture. All right, now I write down what they're wanting me to find, which is a prime. And so I look at my list and I say, okay, I got a, I've got x, I got y. I need an equation that relates a and x and y. Well, clearly that's the area equation of a rectangle. So it's a equals x times y. Now, when I do this derivative, I have to do what? I have to do a product rule. Now, I'm doing the derivative with respect to t. So I do the derivative of a with respect to t. That'd be dA dt, a prime. And when I do the product rule, the derivative of x is 1. No, it's not 1. It's x prime. Right? Because we're doing it with respect to t. So the derivative of x is x prime. We leave the y alone, plus the x left alone times the derivative of y prime. Now look at all that mess we have. Now before we do this, I want to talk about this that we did yesterday. because I felt like people were a little confused by this. So yesterday I had this V equals 1/3 pi r squared h because we had the cone volume. And I told you not to do a product rule here because it would involve an R and an R prime and an H and an H prime and a V prime, and I said we don't want that. Well, heck, it looks just like this problem. We did a product rule. We got an X and an X prime and a Y and a Y prime and an A prime. Why do we want it here and we didn't want it over there, Zach?
Because we have values for X prime, Y prime.
That's right. In this problem, all we knew was V prime. We wanted to find H prime, and we knew H. That was the only information we had. Now, the other thing we did know was that R was equal to 1/4 H, right? We did know that R, the radius, because of similar triangles, the radius was always 1/4 of the height. So what that allowed us to do was to substitute that 1/4 H right in there for R. Then this problem only had V's and H's in it. So when we did the derivative, we'd have V primes and H primes, which we could then plug in and get the stuff we need. So the decision on whether you need to sub or do something like this depends on what information you have. That's the key thing you have to understand. Okay, so in this problem, we had all this information, so we were fine. X prime, we plug in a 2, Y, we plug in a 5, X, we plug in a 4, and Y prime, we plug in a 3. So we had stuff to plug into all these, and that gave us our A prime, which was 22 square centimeters per second. Okay? Because it was square centimeters because it was area. It was the rate the area was changing. All right? So that was the comment I wanted to make. Now we're going to do several. You're going to have a bunch of those to do in your homework today, and I want to give you some work time here in a minute. Okay? All right. Take out your sample 1 packet, please. One more thing I want to go through, and then I want to give you some work time. Sample 1, problem number 3. Now, this was, I think, the only problem in the first 28 that we looked at, or in that first section that we looked at, that we hadn't really learned what to do. Now, although we've probably learned enough, you could have maybe come up with it, especially since it's multiple choice. You could have maybe figured out by kind of elimination which one it might be. But we hadn't really covered this topic. Well, now, when you reread 3 again, so what does this sound like now? It's kind of that related rate thing, right? This thing is changing, the line is rotating, and theta is changing, the angle's changing, so at what rate is the slope changing? Okay, so if we think about our steps on these related rate problems, we would draw a picture, okay? We would label the things, if there's anything changing or not changing or whatever, but it says a line is coming through the origin. It is rotating, creating this angle theta. And we want to know something about the slope of this line. So it's asking about theta, this angle theta. D theta dt, remember, would be the same as theta prime. D theta dt is the same thing as theta prime. Okay? So as this thing rotates, theta is changing, but the slope would also be changing, right? And so what could we label the slope? What do we usually label slope? M, right? So what would be the rate that the slope's changing? M prime. So what they're asking for is M prime. So what we need is an equation that relates M and theta. So look at this picture, and what would relate M and theta? Probably need a triangle. What's the slope? What's our old algebra way of doing slope of line? rise over run. But involving theta, what's rise over run? Tangent. Did you ever talk about that in trig? The tangent of this angle, if you have a line through the origin, the tangent of this angle is the slope. It is, because it's y over x, right? SOHCAHTOA, opposite over hypotenuse, rise over run. So the slope, so the equation we want is m equals tangent theta. That's the equation. Because it involves theta and it involves m, which are the two things we want. Okay? So we want to know what m prime would be. Well, we do the derivative of both sides with respect to t. Let's see if you can get it. So what's the derivative of the left side? M prime. Good. What's the derivative of this side? Okay. Where'd you get that? What's the derivative of tangent theta? No, that's not how we learned it. The derivative of tangent is secant squared theta times theta prime, right? We're doing the derivative of both sides with respect to t. So just like we were doing our x, y ones, we got tack on an x prime, a y prime, an r prime, an h prime. Here we got tack on a theta prime. We're doing the derivative with respect to t. Now, what's secant squared? 1 over cosine squared. So there it is right there. 1 over cosine squared theta times d theta dt. That's the theta prime. Okay? And that's where that came from. So that was a related rate kind of problem with a little trig thrown in. You had to get this rise over run thing pretty much. Okay? And that's kind of a tricky problem. Because you've got to somehow make that connection with rise over run and slope, the tangent. But I think if you draw a picture, I don't think it's that hard. And if you look at the different choices here. Okay, so that was one I wanted to do. And while we're at it, we got enough time here to do one other one. Does anybody have another one in there they really, really wanted to see? Carrie, you're up. What do you got? Huh? 22. Oh, this one was easy, wasn't it, man?
Yeah, but it's the one with the
It's what? It's the one, yeah. Okay. So this, okay, first of all, what's this first thing to say here? And so how can I write that? I can write that y prime, right? I mean, that's how we're used to writing it, but dy dx, same thing. So they're telling me y prime equals x squared y squared, and what are they asking me for? That's y double prime, right? You got to understand that notation. I just mean y double prime. The 2's just mean second derivative. They don't mean squared or anything. They just mean second derivative. Okay? Where it comes from is this. It's saying do the derivative of the derivative, which is what second derivative is. Well, if you look at that, you kind of see where they get d squared y over d x squared. Right? You kind of see where the d2y, that's where it comes from. It's just saying do the derivative of the derivative. So it's second derivative. So what could we do to this right here? Do the derivative of both sides, right? With respect to x. Now, we're not doing it with respect to t. So we're not going to tack on any x prime derivative. We're doing it with respect to x. Okay, so the derivative of y prime is y double prime. Do a product rule here. Derivative of x squared, 2x. Y squared left alone. X squared. 2y. Y prime. So now you look, you say, okay, second derivative. Oh, what's the matter? There's no y prime in any of the answers. When we did implicit differentiation, we didn't do any second derivative on that. We might have done one. Same. So I did. So that's right. So take that and just substitute it right in there for the y prime. So we got y double prime. Anytime you do an implicit differentiation, you have y prime equals something, so you do the second derivative, you get y double prime. When you do the second derivative, you're going to get a y prime in there as well. Well, you always will have y prime, so you substitute it in. So we get 2xy squared, and then this would be x, this would be 2x squared y, and with an x squared, y squared thrown in. So that would be 2x to the 4th, y to the 3rd, which is this volume, just in a different area. Okay? So that's just a implicit differentiation example with the product rule, and then with that twist where you gotta take the y times and substitute it in different areas. Okay? All right. So for our homework, and you'll get the last almost 40 minutes to work here, we're going to do a kind of a combination of things. So in the business packet, so depending on what you think you need the most help with, maybe work on that here in class so you can get help from each other or ask me. In the business packet, we're going to do 21 and 23. Okay, and those are optimization. Those are max or min ones. All right, and then in the book, in section 4.5, these would be related rate problems. We're going to do 10, 12. Make sure you go to the right section. Now, I didn't check the page number of these. I think it's like 254, I think. 10, 12, 16, 23, and 26. 10, 12, 16, 23, and 26. Now, that's basically your homework for tomorrow. So some related rates, some optimization. You also should begin working more in this sample pack. Okay, we did, the first section had 28 questions, but about 18 of them were circled. And we kind of went through some of those, and hopefully you've got most of your questions answered on those. Now there's another section that's the calculator multiple choice, and some of them again are circled. Those are the ones to do. And then at the end there's some free response questions. Some of them are calculator, some of them are not, and some parts are circled and some parts aren't. So just the circled ones, all we're doing. Okay? So begin to go through that, but because at the end of the week we want to have this sample one done, I'm going to give you another packet. Okay? So probably each night you should probably go through and work a couple, 2, 3 or so of those problems. Okay, just trying to gradually work your way through so you don't find yourself at the end having to do a whole bunch of the packet. Okay, so work on the homework. Now we're going to have some work time over the next couple days each day like this, at least a half hour or so I would say, in class to be working on these and then but also in that sample. Yeah. The quiz will be Friday. There really isn't a whole lot new to do between now and Friday. There's a lot of practice. And we do have to go back and review that paramedics. Okay? All right, so let's work on, you got the rest of the time to work on those. And then don't forget about that sample packet too.
I think it's restaurant.